Welcome. So this is 48B video 3. Let's talk about interpretation of graphs of displacement, velocity and acceleration. Okay, so here I have three graphs. One is a let me get my pen. One is a coordinate or position or address versus time. The other one is a velocity versus time, and the third one on the right is an acceleration versus time. So first warning, people tend to not look carefully enough at the axes of a graph. My sense is that if I ask a question about velocity-time relationships, and the next question is a graphical question, some students will just seem to assume that the graph is velocity versus time. But it needn't be. It's a different question. So always make sure you double check what the axes are on a graph, because the way you interpret the graph depends upon the axes. And some people even go as far as highlighting. You know, they'll get a highlighter and they'll mark it so that people know, oh, this is a velocity versus time graph. I know what I'm talking about. People, you know, once you've been bitten, you don't want to be bitten again. The two things to ask yourself with, well, the three things to ask yourselves with the graph is, what can I get by reading the graph? So with this, I can get position by reading the graph. And with this one, I can get velocity by simply reading the graph. And this I can get acceleration by simply reading the graph. The next question is, well, what does the slope represent? And the way you get that is you ask yourself what the units are. If I have a rise over run, well, in this case, the units for the rise would be in meters, and the units for the run would be in seconds. Meters per second, it's a velocity. So the slope of a position versus time graph gives you velocity. In this case, it would be velocity and seconds. Meters per second divided by seconds is meters per second squared. So this would be acceleration. And for this third graph, the slope would be meters per second squared divided by seconds, which is meters per second cubed. And up here I say no clear meaning, and that's because I had my physics hat on. It actually is the rate of change of acceleration. And because acceleration is linked to force, it's the rate of change at which you apply a force. And that's the process of jerking something. If you walk up to a piece of furniture and you suddenly push it hard, you're increasing the force on that object as time passes, which is increasing the acceleration of that object as time passes, which is jerk. So this would be jerk. If I look at the area under the graph, then it's going to be, in this case, meters seconds. And meters seconds, no clear meaning. It exists, but we don't find it useful to think about. In this middle graph, on the velocity versus time graph, it's going to be meters per second times seconds, which is meters, which gives us displacement. And if I look at the area of an acceleration versus time graph, it's meters per second squared times seconds, which is meters per second, which is velocity. So this is reading, this is slope, and if you like, this is the integral. These journeys, these graphs, are not giving you information about the same journey. If you have this position versus time graph, you do not get this velocity versus time graph. They don't go together. I just picked them because they were typical straight line graphs. Okay. Let's do some questions. I'm going to review a little bit from the last video first of all. An object has a velocity of -6 meters per second equals velocity, and an object has -2 meters per second squared equals acceleration. So characterize the direction of motion. You always go with the velocity, so that's going to the left. And characterize the rate of progress. Is it speeding up or slowing down? Both velocity and acceleration are pointing in the same direction, so it's speeding up. Now, thinking about these graphs, what is represented by the slope of a velocity versus time graph? So here's my velocity and here's my time, and let's say I have a graph. Then the slope will be change in velocity, which is delta v, and my change in time, which is delta t. Well, my acceleration is equal to delta v over delta t. So the slope of a velocity versus time graph gives us acceleration. And it would be meters per second divided by seconds is meters per second squared. Cool. So here are some journeys. Again, these three journeys are not related to each other. They're just three examples. And I'm just trying to get across to you at this stage the fact that they're all useful, but we interpret them differently. And sometimes, to get the same piece of information, we'll do it in a different way in the different graphs. So the first graph, of course, is position versus time. And the first thing to ask yourself is, well, what do I get by reading the graph? And if I simply, project a point up in time, say half a second, I find I have my position. So this, by reading, will give us our position at a given time. And this graph, by reading, will give us our velocity at a given time. This is the middle graph, the velocity versus time graph. And the right-hand graph, which is acceleration versus time, well, if we simply read the graph, we'll get acceleration. What is the acceleration at this instant in time? Fair enough. Let's go to the next stage. Well, what does the slope give us? Well, clearly the slope on this left-hand position versus time graph, it gives me meters per second, which is velocity. So I can read the average velocity for the first second. I could read the average velocity for the first 5 seconds. So I said, well, there's my change in position, -30, and there's my change in time, 5. So my average velocity would equal -30 over 5, which equals -6 meters per second. For my velocity versus time graph, I can look at the slopes and I can say, well, in the first 2 seconds I had a rise of +5 meters and a run of 2 meters. So that would be a acceleration of 5 divided by 2 of 2.5 meters per second squared, and it's positive. It's a positive slope. Or again, I could say, well, what's the average acceleration between 2 points in this journey? And I could say between time t equals 2 and t equals 5. And I would say, well, my rise is -15. So A in this case is equal to -15 over my run. And my run goes 2 to 3 to 4 to 5. My run is 3, which equals -5 meters per second squared. And I could look in this third graph, the right-hand graph, acceleration versus time, and I could say, well, what's the jerk during the period between 2 and 4 seconds? And I would say, well, my jerk, I don't have a symbol for that, I'm going to call it a jerk, is equal to my rise over my run, which is minus 5 over 2. There's my minus 5, and there's my 2, which is minus 2.5, and this would be meters per second cubed. And again, I could say, what's the jerk between 0 seconds and 5 seconds? We can play those games. Let's get rid of this, and then let's ask ourselves about the area under the graph. If I ask myself about the area under the graph, let's be careful here. It's not to the bottom of the page. If I said, what is the meter seconds in the first 2 seconds, I'd look at the area under the graph. It wouldn't have a physical meaning, so I would never ask you this question, but it does exist. Let's ask you what the displacement is from this velocity time graph in the middle. Let's say, what's the displacement in the first 3 seconds? So you'd say, well, there's my area, and I would say my displacement is equal to, and it's going to be, well, there's a triangle. This will be a half. The base is 2 seconds times the height is 5 plus 5. And then we have a trapezoid. So it will be a half times the left hand side, which is plus 5, added to the right hand side, which is plus 15, times the base, which is in this case 1. Put a bracket around that so it's complete. So my change of my displacement is equal to 5 added to, well, 5 plus 15 is 20, and a half of 20 is 10, so that would be 15, which equals plus 15 meters. Cool. Now, just to recognize, if I went from 4 seconds to 6 seconds, recognize that that part of the journey would be a positive displacement, and this part of the journey would be a negative displacement, and you'd add them as positives and negatives together. And if I wanted to know the jerk on this right hand graph, I would do the area under the graph as well. So it's a nice system. So you need to be able to read the graph, you need to be able to understand what the slope gives you and how you'd work out what that parameter's value is, and you need to work out what the area under the graph gives you and what that parameter's value is. There's some other things that are a bit more colloquial, so let's just briefly mention those before we go on, and that is this. Colloquially, I could say on this first left-hand graph, the position versus time graph, so when do you stop moving for the first time? Well, okay, so we're moving, and then we stop moving here. Can you see how there's no change of position? That's being stationary. And I started that at 1 second, and I ended that at 2 seconds. So when you want to know when you stop moving, when you're stationary on a position versus time graph, you look for horizontal slopes. That's not the case with the velocity time graph. With a velocity time graph, the horizontal slopes actually give you constant velocity. With the horizontal time graph, I need to look for places where the graph crosses the axis and has a 0 value for velocity. Now, it's only stationary here for an instant, but it's still got zero velocity. Another thing I could ask you is when you turn around for the first time. So for instance, in this position versus time graph, I'm going in a positive direction, I'm going stationary, I'm going in a positive direction, then I'm going into a negative direction. So I turn around here for the first time when I have a change of slope from positive to negative or negative to positive. There's a change of direction between there and there. But on a velocity versus time graph, I change direction when I go from the positive velocity axis to the negative velocity axis. So my change in direction is when the graph crosses the axis. Can you see that these graphs take practice so that you interpret each graph the correct way? It's easy to apply the rules for a position versus time graph to a velocity versus time graph and to misinterpret the graph. We say we can interpret these graphs to determine things like object's position and direction of motion at a specific time, an object's average velocity, distance traveled, displacement during part of the journey, when an object stops, the maximum speed, the maximum velocity, and many other things. There's probably 30 questions I could get out of a series of graphs like this. So please make sure you focus on this for a little bit. Here's some examples. So first of all, what kind of graph is it? And it's a position versus time graph. Okay. And then the second thing I say is, what is the object's direction of motion at t equals 6.5 seconds? So I find 6.5 and I extend it up, and now I'm here. Now this is a position versus time graph, and I'm being asked about the direction of motion, and the direction of motion depends upon velocity. Okay, I need to find something about velocity from this. Oh yeah, the velocity is given by the slope of a position time graph. That's a negative slope. That's a negative velocity. So this would be, what is the object's direction of travel? It would be negative, or to the left if you like. It would be negative or to the left, because that slope is negative. Another way of intuiting the answer is to say, well, I start off a little bit beyond, I'm at plus 30, and I end at plus 20, so I must be going in a negative direction. So you can get it by visualizing, but you can get it more formally from the math. What is the object's average velocity between 1 and 4 seconds? So for that one, between 1 and 4 seconds, we go to where we are with 1, go to where we are with 4, draw our line. I know my velocity is my slope. My rise is equal to 0 minus 20, which is plus 20 meters. And my run is 4 minus 1, which equals 3 seconds. So I would say that my velocity is equal to plus 20 over 3 meters per second. Be nice if that worked out as a whole number, but it didn't. I'm not going to worry about it. Okay. When does the object stop for the first time? Position versus time. Let's erase a little bit here. When does the object stop? Stop changing its position. The object stops for the first time here. And the answer I would put down for this is, I would say, well, it stops moving at plus 1 second. It's the beginning of it. And then what is the object's instantaneous velocity at 5.5 seconds? Well, here we go, 5.5. I draw a tangent to this graph. It's horizontal, 0 meters per second. Can you see how we know how to do the bits? It's just that I can dress things up colloquially. Let's look at this next one. In this next one, what is an object's direction of motion at 4.2 seconds? So at 4.2 seconds, I'm in here and I look up here. Now, I have a negative slope, but the fact is I have a positive velocity. I'm being asked about direction of motion, which depends upon velocity, and so I got to look at the actual reading of the graph. And I see it's a positive value, so this will be a positive direction. So in this case, because it's a velocity versus time graph, I simply read the graph to get velocity, whereas previously I looked at the slope. Can you see how it gets confusing sometimes if you're not careful? What is the object's average acceleration between 2 and 7? So here's 7, and here's 2, and here's my triangle. Remember that acceleration is the slope. This is minus 20, and this over here is going to be 5. So this is going to be minus, so my acceleration is equal to minus 20 over 5, which equals minus 4 meters per second squared. So when does the object stop for the first time? And let's erase what we have. So when does the object stop for the first time? I'm looking for a time on here where my velocity is 0. And that's where it stops for the first time. Now here's the interesting point. People will sometimes say 4.5, between 4 and 5. This is an engineering course, and we need to be a bit more precise than that. If you notice, from the top of this line to the bottom of this line is 1, 2, 3, 4, 5 steps. If there's 5 vertical steps and it's a straight line, there must be 5 horizontal steps. So that second should be divided into fifths. And if the point I'm interested in comes after the 3rd vertical step, it comes after the 3rd horizontal step. So for that one, it would be 4.6 seconds. Not 4.5, not 4 and a bit, it's 4.6. And in a test, I would say, when exactly does the object stop for the first time? And you'd put down 4.6. Now recognize it stops for an instant. It doesn't stop and stay there. And then what is the object's displacement between 2 seconds and 3 seconds? Let's clean up a bit. Between 2 seconds and 3 seconds. So here's 2 and here's 3. And that's a trapezoid. And a trapezoid says that the area is equal to the average height. So that's a half of h left plus h right times the width. So if I look at this, it would be 1/2 of 5 plus 15 times the width, which is 1, which equals 20 divided by 2 is 10, times 10 is 10, times 1 is 10. So that would be 10 meters. Plus 10 meters because it's above the axis. Okay. Remember, you don't go to the bottom of the page on these questions. Cool. And so next, this is more like a test question. So let's look at this. What is the object's average velocity between 2 and 4 seconds? So let's have a look and see what graph we have. We have a position versus time. So I'm going to find the average velocity by looking at the slope, and between 2 and 4 seconds means I go from there to there. So there's the slope I'm interested in. The value is the rise over the run, and this is plus 15 and this is plus 5, so that's plus 10. And this is 4 and this is 2, so that's plus 2. So the value, the velocity, is going to equal my rise over my run. My velocity equals plus 10 over plus 2, my velocity equals plus 5 meters per second. Answer C on that one. And then when does the object stop for the first time? Let's clean up. So again, I'm looking at so again, let's just, pedantically, but let's just double check. I've got a position versus time graph, and I want to know when I stop from the first time. I stop when I stop moving. And I'm moving for the first 2 seconds, and I'm moving for the next second. I stop moving there. So I would say on this answer, this would be 3 seconds. I stop moving at that point there, and it's 3 seconds. Notice it's not here. That actually is when I return to my starting position, which is another question that can be asked. Cool. Another little bit. What is the object's displacement between 3 seconds and 6 seconds? It's a velocity versus time graph. The displacement of a velocity versus time graph is given by the area under the graph. So I need to go from 3 seconds to 6 seconds. And my displacement is that bit there, which is all negative. And then this bit here, which is positive, and that bit there, which is positive. And I recognize that there's 2 triangles and a rectangle, so I go, it's a half the base, which is 1, times the height, which is 30. If you like, you can call it minus 30, and you've already taken care of the negativity of that region. And then we look at the next section. It's a triangle, so it's a half, and the base is again 1, and the height this time is plus 30. And then I have the last little bit, which is a rectangle, so the base is 1 here, and the height is plus 30. So when I look at this, this is going to be my displacement. So my displacement is equal to, well, this first section here will cancel out with that section there, and you can see it on the diagram that they cancel each other out. So my displacement is going to be plus 30 meters, and there's my answer, plus 30 meters. Cool. And then this next little bit, when does the object stop for the first time? Now again, let's clean up a little bit. Again, let's remind ourselves we're looking at, let's just get our marker. We're looking at a velocity versus time graph, and I'm stopped when my velocity is 0, and so I'd look along the line, I'd go, well, I'm stopping, ignoring the start, I'm stopping for the first time instantaneously at times t equals 4 seconds. This is a constant high velocity. This is a constant negative velocity. But on the position versus time graph, they would have completely different meanings. Can you see how it's easy to get them confused? Watch out for it. The thing about this section is that it's really delightful in some ways, but it's easy to get things confused. It takes a lot of practice. There are a lot of questions that I can ask from one diagram. So don't try to remember how I solved the problem, because you'll probably never see it again. Try to remember my approach. And there we have it. Thank you.